morning, good morning, good morning, fancy meat computers. Oh, I just woke the baby. Whoops. Sorry. There he is. Whoop. There he is. And there he goes. Well, good morning, everybody. How is everybody today? Hopefully you're doing alright. That's the cardinal sin of early parenthood, by the way, is waking the baby. You know that somebody has actually had kids when they deal with the concept of waking the baby with the reverence due to, like, third or fourth level mystery of like a Hellenistic cult. I told you guys, when I get 1,000 subscribers, you can see the baby. No, we're not going to do a baby unboxing. Yeah. Right. So, anyway, let me see. I think we probably don't have any announcements, but I'll check. Anyway. Boop. All right. All right. There we go. So, yes. Nope, we already talked about the A1 submissions, so that's fine. Love me a cup of the tea in the morning. All right. So, might as well tick off all of those people who always show up late for class and begin not too far into the actual class. Sounds like a good plan. So, last time we were talking about if statements. We finished off talking about if statements. We talked about various things. We talked about how one goes about structuring the most basic of loops. And now we're going to talk about how one structures if statements and branching if expressions. So I said last time, and I will hold to this, that branching your program correctly is one of the least difficult things to accomplish in a program. Like, from a beginner's perspective, most people get if statements pretty intuitively. Loops are a bit more tricky, but as long as you've got a good handle on the syntax, you should be able to accomplish both of these things with relatively little difficulty, at least for basic examples. The whole idea, the whole development of the whole programming skills thing, is the application of if statements and loops to ever-increasing problems, problems of ever-increasing complexity. So, I'll let you in on a little bit of a secret about programming. This is kind of like advanced programming knowledge that you typically wouldn't see until second and third year. But here we go anyway. With programs, all programs are reducible in one way or another to if statements and loops. If statements and loops are the conditions by which a programming language is considered to be Turing complete, which means that it's Turing equivalent. That's another way of saying it, which means that you can express any program that you write using if statements and loops as a Turing machine. Alan Turing, of course, one of the grandpappies of computer science as a discipline. Turing stands in relation to the discipline of computer science in much the same manner that you would have like Isaac Newton or Albert Einstein standing in relation to the field of physics. Probably more of a Newtonian kind of a guy than an Einsteinian kind of guy, because Newton laid the groundwork, and then Einstein said how Newton was wrong. So, Turing is kind of like the guy who laid a lot of the important theoretical foundations. It's kind of interesting. There were a number of models of computation that were competing at the time. It turned out that the Turing machine was the one that was most directly implementable in terms of electronic circuits. So that's the one that got implemented first, and because it worked, people kept iterating on it, and all of these other models of computation are all now simulated on these machines that are fundamentally based on the ideas put forward by Turing. When you get into the third year course, you'll, like my third year class is right now learning about lambda calculus, which is actually a whole and complete alternative to the Turing machine that was developed by Alan Turing's PhD supervisor, Alonzo Church, in the 1920s, and it's an equivalent model of computation to the Turing machine. So anything you can express as a Turing machine, you can also express in lambda calculus, and vice versa. And this kind of interchangeability of languages is a feature generally of programming languages. Basically, like any Python program can be expressed as a C program, can be expressed as a Visual Basic program, a Java program, a PHP program. I'm not sure. I've never really used PHP. Unless it's a really restrictive domain-specific language, all general-purpose languages can express each other's programs. And the reason this works with the interoperability of programs between imperative languages is due to all languages have if statements, all languages have loops. And between these two constructs, you can construct anything. In other types of languages, like you guys will be doing functional languages, 1JC3, you guys will you'll be doing functional programming as well, and the way that functional programming gets to claim to be Turing complete is that it has infinite recursion instead of infinite loops. Like, being able to produce an infinite loop is a condition of Turing completeness. So yeah. Long story short, the single fundamental skills of programming, from which all other skills in programming are built, are if statements and loops. So please pay attention to this if you're a person who's taking programming for the first time. Dr. Farmer was one of the so Dr. Farmer is so if you're not familiar with how academia works, it's like you have lineages, right? You have supervisor-student. It's like a mentorship relationship. So you have academic lineages that go all the way back up into history, right? So yeah. So Dr. Farmer is a direct descendant of Alonzo Church and therefore Alan Turing. Well, actually, no, I shouldn't say that. Alonzo Church, yes, but he would have to be supervised by someone Turing supervised in order to be descended from Turing. So that's probably wrong. Because I'm not sure that Turing... I don't know if Turing ever had a professorship, to be honest. But anyway. Yeah. How do you convert between the syntaxes of languages? Well, that's an interesting question. Most of the time, if you just want a program done, you do it by hand. But there are a number of tools that you can build that look and they smell a lot like compilers. But a more accurate term would be translator or cross-compiler. So, yeah, that's... basically, you could have a compiler that compiles to, from Python to C. Frankly, that's pretty much what the Python compiler does. But, yeah. So anyway, if statements. We were exploring the concept of using the else if to be able to chain together multiple conditions and thus expand the branchability of our programs. One of the very, very critical and key observations that you need to make about programming at some point is that when you have a statement S, this statement S can be anything, right? It doesn't just have to be assignment. It can also be if statements. It can also be loops. You can have loops inside of if statements. You can have if statements inside of loops. Oh, did he say he was a descendant of Turing? That's cool. Awesome. When you're a PhD student, you get a little bit jumpy about making claims that you can't prove. So if he said that he's a descendant of Turing, then that's awesome. But, just because he's a descendant of Church does not mean that he's a descendant of Turing, right? Because he could have been a descendant of one of Church's other students. Other less prominent students, shall we say. So I didn't want to claim it if I had no evidence for it. Oh, we've got some disagreement in the chat. Okay. Well, I'm not sure. You would have to ask Dr. Farmer about his own provenance. So, that can be our word for the day. Provenance. Divisibility. So, let's go through an example. A few examples that have to do with if statements. Ah, yes, okay. Yeah, like, Turing kind of had a rough life. The thing about Alan Turing, he Alan Turing died in his 30s, like mid-30s, because I believe he committed suicide because of chemical castration that he was forced to undergo because he was gay in a time when it was illegal to be gay, which, generally speaking, if you're both gay and a time traveler, you should probably travel forward in time, not backward. If you're looking for people to not legally sanction you. So, he didn't have a especially long life, and normally in order for someone to have, like, students and generations of students, you have to live a bit longer than your 30s. I don't even know if he achieved tenure, or, I don't really know that much about his life, but, or at least his later life. Everybody knows about the Nazi thing, but yeah. I don't need a fancy descent. What about me? I don't know. My supervisor is Dr. Lawford. I'm not sure what Dr. Lawford's prominence is. To be honest, we've never actually talked about it. I've been his student for like a decade, and we have never actually talked about the provenance. So, that's interesting. Yeah. That's a speculation. People think there was motive for murder. Ooh. Yeah, so there was, I'm sure a lot of you will have seen this movie, but if any of you haven't seen the movie, it's the Imitation Game, I believe is the name of the movie. And it's a biopic starring all of the traditional Hollywood people, etc. So, it's not exactly an art house film, but it's still a very interesting movie if you're interested in the history of computer science. But anyway, we should continue on. I've been gabbling again. Yes. Ugh. The thing to keep in mind about any biopic is that they're going to be making a certain amount of the story up, right? They'll be making themes that never existed in the person's life. That's kind of like a part. It's not a bad thing necessarily. It's part of the act of dramatizing someone's life. Is you're trying to create themes and connect up themes that, if you actually asked Alan Turing if some of the themes in the movie were themes in his life, he would probably be like, maybe, I guess. You think so? All right. It's like Doctor Strange was Alan Turing. Really? Is that okay? I need someone to fact check that for me real quick. If Doctor Strange was Alan Turing, or no, it would be like a dramatization of him. Like, are you talking Doctor Strangelove? My God. Oh no, Doctor Strange from the Marvel movie. All right. For one brief moment, I thought somebody in this class was aware of the movie Doctor Strangelove. Which, if you like old movies, and you haven't heard of it, then you don't like old movies that much. Anyway, so here we go. So if statements. Write a function that determines whether a number is even or odd. Yes, it's Benedict Cumberbun. It's Benny Boy Cucumber Patch. So, anyway, let's open up a let's do some coding, shall we? Stop talking about movies, for Christ's sake. So, I'm just gonna get rid of all that. So, so it's kind of funny. An interesting way to determine if a number is even or odd is using the modulus operator. The definition of an even number is that an even number is evenly divisible by 2. So, if we have n mod 2, equaling 0, then we know that our number that we input must be even. Otherwise, it's odd, because a number may only be even or odd via the definition of numbers. So, if we print even odd 5, and if we print that for 10, and then we execute, the first one is odd and the last one is even, as you might have imagined. Pardon me. Benadryl Cucumber Patch. There we go. Yes! It's Doctor Strangelove, or How I Learned to Stop Worrying and Love the Bomb. It's about nuclear annihilation. Roughly, the plot of the movie is that the Russians build a doomsday weapon, but they don't tell anybody, which is stupid, because the whole point of having a doomsday weapon is that you tell people so they don't attack you, and some person who's mentally not all there is in the Air Force in the United States Army and sets it off, and yeah. What would happen if you put -10? Good question. Let's run it. Gotta save it, though. -10 is still an even number. So there you go. Which is true, as it turns out. So, write a function that determines whether a number is divisible by 2, 5, or 10. So, here we go. Let's modify our algorithm slightly. Let's add an if case, an elif, right here. N mod 5 equals 0. So this tests divisibility by 5. Elif n 10. So this is by 2. Return by 5 and by 10. 0 is also an even number. What happens if you put a all right. If you have a floating point number in there, it won't come out evenly. So it won't be exactly equal to 0, so it won't work. This only works on integers. Yes, 0 is an even number, because when you divide 0 by 2, you get 0. That's how 0 works. All of your math intuitions, generally speaking, apply when you're programming. So, this is now called divisibility as well. Divisibility. So, do you see how I, like, restructured that program to, you know, serve a new purpose relatively easily? That's something that you can do in programming. So, I should have kept a copy of the old one, though. So, when we try the divisibility by 5, we get by 5. And when we attempt divisibility by 10, we get by 2. So 10 is an even number, so we're not surprised that it hits this case. But here's a question. This tests divisibility by 2. This tests divisibility by 10. So why didn't we get by 10? Right? So as some of your astute colleagues in the chat have pointed out, 10 is divisible by both 2 and 5. So if we check that if it's divisible by 2, like 10 is divisible by both of these, the thing to understand about if statements is that we still have the implicit ordering going on. So the first condition is checked first. The second condition is checked second. The third condition is checked third. The second and third condition are not checked if the first one passes. Similarly, the third condition is not checked if the second one passes, which can only be checked if the first one does not pass. So that's the case with divisibility by 5. So that's how an elif works. You go through the conditions one at a time, checking each one, and if it comes out true, you execute that function body, and that's it. That's it. It does, especially, like, in this particular case, it especially finishes because any return statement will terminate execution inside of a function. But we don't have to necessarily do that that way. We could also do, like, x is none, x is equal to by 2, x is equal to by 5. There we go. And then return x. So return statements exit automatically. So it was kind of like a dummy example, but I'll show you that this still works if it's just regular assignment statements that you're using. There you go. It still works. So. You should allow fall through. You don't get fall through on if-else constructs. That's the whole point. What would the function look like with a floating point number? Well, you can't really... It doesn't work with floats. You don't get even divisibility by floats. So this algorithm is not applicable to floating point numbers. It would just... Like, you would get none each time. Like, if I did 5.2, for example, and ran that... Oh. Wait, did I save? I didn't save. There you go. You'd get none. So with floating point numbers, even if it's something like 5.0, it's like a toss-up whether you would get it returning by 5 or by none. So it does 5 in this case. But you've seen previously how floating point numbers can be tricky. They might not be what they say they are. So you have to always be careful with floating point numbers. Do you have to define x as none at the start of the function? No, but that's a good decision, right? So none is like, if none of these happen, then the value at the end will indicate that none of these happened by saying none, right? This is a construction that's similar to what we call flagging. So sometimes you want to create what's called a flag in your code, which is you set a variable here at the top. Inside of your control structures, you set that to a different value if something you're interested in happening happens. And then at the end, you can read the flag to see if the thing that you were interested in happened or not. Like, for example, if you wanted to very quickly say x is equal to false, let's say the thing we want to see is if the loop exceeds 10 iterations, right? So while I is less than, 20, if I is greater than 10, x is equal to true, and then at the end you print x. And that'll tell you if the particular thing you're interested in happened while you were inside of the loop. So there you go. Can you just directly use print statements for printing by 2, by 5, by 10? Yes, you could, in theory. However, in general, we're trying to get you guys away from using print statements and input. We're trying to get you away from using the print and input functions to handle I/O and trying to push you into using function arguments and function returns in order to perform I/O, because that's much more useful, and like real programmers don't handle that kind of a real programmer knows that the input is the arguments and not the results of the input function. But yeah, so if you use all ifs, no elifs, then it will show that 10 is divisible. But yeah, so that's an interesting thing. So if I remove the L, so if I just make this 3 sequential if statements, we do get a difference in functionality. That's an interesting point. Yes. In that case, we get by 5 by 10. And the reason for that, when we run divisibility 10, x is first assigned none. This condition comes out true, which means x gets assigned by 2. Then it also tests this one. Instead of skipping to the end, it'll test every single one. So n mod 5 by equaling 0 is false, but n mod 10 is equal to 0. So the value of x will be overwritten by 10. And then we return it, so there you go. It will return by 10 in that case. So what the L does is it makes it exclusive. Only one of these conditions is permitted to execute. Whereas if you remove that, all of them are permitted to execute if their conditions come out true. Real programmers use argc and argv. Yes, they do. Would you generally stay away from having multiple return statements in one function? That's an interesting general stylistic point. In general, if you're a beginner, it's recommended that you restrict yourself to one return statement. But I can tell you right now, as a matter of practicality, this particular programmer will often use multiple return statements within a function just for the convenience of it. But yeah, so it's overwriting it. Yes. Yeah. So, yeah. The number, it's like a return statement is two things, right? It specifies what you're returning from the function, but it also immediately terminates the function, right? So it's like an exit command as well. But, yeah. So, we have a couple of iterations on this. So what would happen if we put the 10 at the top? You guys probably are. There you go. So what if we swapped the position of n div 2 or n mod 2 and nmod 10, what would happen? Let's take a look. Save that up. We get by 5 by 2. What? What happened? Where did it go? Where did div 10 go? There. There we go. By 5 by 10. Because in this case, 10 is being tested first, right? So if it falls to this case, we don't test this one. Right? This would make more sense. Saying that something is divisible by 10 is more specific than saying it's divisible by 2, so this, arguably for the user, this would be more useful information. Yes, 10 mod 5 is equal to 0. That's true. So, just very quickly on argv, argc, you'll see this when we do 1xc3 if you decide to take it with me. But if you provide command line arguments like python3 topic 3.py some arguments, those arguments will get stored in argv and argc and are readable to your program. Argv tells you the what the actual it's a list of strings in Python that gives you what the arguments you entered in were, and argc gives you the count, how many arguments you had. But yeah, argc doesn't really it's not really that useful in Python, because in Python you can just call length on the list of arguments that are returned, so it doesn't really matter. But that's getting away from what we're talking about here. So, how about this? What if we did this? What if we said, let's do let's iterate on this, shall we? Divisibility 2. We're gonna do a sub-if statement. N mod 10 equals 0. Then it's by 10. Else x is equal to by 2. And we'll delete this case because we don't need it anymore. There! So, if something is divisible by 10, it is also divisible by 2, right? So, in this case, this is equivalent functionality. We still get by 5 by 10. And if we had, like, by 8 in here as well, we get by 5 by 2 by 10 by 2. So yeah. Yes, and the other way that you could do this, incidentally, is you could say something that's divisible by 10 is divisible by both 2 and 5. So you could just do divisible by 2 and divisible by 5. This is how you combine tests using a Boolean operator. So this would also work. I'm not sure why you would do this, because it's like simpler and easier and quicker to write mod 10, not mod 2 and mod 5. But yeah. I'm still running the divisibility. Oh, yeah, wait, yeah. Sorry, yeah, thank you. All right, it'll be the same output, but there you go. Now I'm running the correct function. Thank you very much. So, the next part is kind of boring, so I'll try to skip through it quickly, because we've got, you know, we got to keep moving on this stuff. So, Spectre. We're going to talk about a bug that existed inside of AMD CPUs a number of years ago. In order to understand the Spectre bug, you have to know a little bit about branch prediction, memory caching, and timing. So, essentially, this is what... So, with respect to optimizing computers, ever since we've been hitting up against the physical limitations to how small you can make a computer, how small you can make the circuits in a computer. If we go much smaller than the circuits we currently have, then we start introducing like quantum effects and electron tunneling, and basically things start. Yeah, some people be. This won't make a lot. This won't be super interesting to like the new programmers, but So basically, Moore's law is more or less now at this point broken. We've hit the point of diminishing returns when it comes to the number of transistors that you could squeeze onto an area of CPU. This is why CPUs have gone to, multi-core CPUs rather than, like we had single-core CPUs up until, about 10, 15 years ago. Then we started having to diversify into multi-threading environments because we're hitting physical limitations with single-core CPUs, right? So basically, the CPU manufacturers have been trying to think of different ways to make things go faster without necessarily needing... just relying on like raw computational power. Am I related to Gordon Moore of Moore's Law? No, actually, no relation. But if it makes you feel better about me, then you can think that. But no, I'm not aware that I'm related to Gordon Moore. I mean, in theory, he and I share the same last name, so that means we must be related in some way, But then again, probably we're related at, certainly 5 degrees of separation, right? And you don't only need 7 degrees to hit anybody on the damn planet, so... yeah. So anyway, one of the things that these CPUs... Now that they're primarily interested in multiple CPU cores. See, the thing about multiple CPU cores is that it's not obvious how you break tasks up between them. So if I show you what's going on in my system right now, right? So this is a program called HTOP, which I apologize for the it's not great, the coloration, but you can see my, this laptop has 16 cores, and you can see that some of them are being utilized at 15%, some of them are being utilized at 0%, and it's sort of a non-trivial problem to design your operating system and your operating system, your kernel, that sort of thing, to take full advantage of multiple CPUs. Yes. So the it's a lot of math, and basically, when we started running into the issues of parallelism, we no longer could rely exclusively on mathematics that were developed from the 1920s through the 1960s. We started needing bigger and better maths to be able to deal with it. So one of the things that a few years ago, one of the AMD one of the things that AMD CPUs started doing was a thing called if statement branch prediction. So basically, it's like a form of look ahead. In the program, the CPU sees there's an if statement coming up, and it's I don't know whether this is going to evaluate to true or false just yet, right? I won't know what what it's going to evaluate to until I get there. But what I can do is I can predictively execute both of these branches so long as certain conditions are maintained and upheld. I can execute these two branches before I get to them on my distributed CPU cores. Like, I can use a different core to branch predict, the left branch and the right branch while I'm still working on getting there. And then once I get there, I don't have to then execute the particular branch that I want to execute, because I'll know the results of it executing both of them. So I just pick the results that corresponded to the branch that now would have executed. Right? Does that make sense? Hopefully that makes sense. So anyway, this is called branch prediction, and that's I believe it's something that they still do. So, if branch prediction was wrong, the CPU resets all of the variables and runs the other branch, but then continues as normal. So, just to remind you of our von Neumann architecture, remember, central processing unit, memory interacts with a memory unit. Very important. It's important for you to distinguish the memory from the CPU in your minds. Like, we'll get into this a lot more when we get into C. But yeah. So in our program, the if statements were essentially calculating at the same time. Yes. It's kind of like... So, generally speaking, a software guy doesn't worry about this type of hardware acceleration. And as we're going to see with the Spectre bug particularly, that ended up biting a bunch of people in the ass. But yeah, it's like... Okay. So I'm going to unveil one of the hard truths of science and science education. Throughout your entire science education, all that you've been given is a series of increasingly high-resolution models of how things work. This is how we educate people in science. It's like, when we started off, like, if you were in elementary school learning the water cycle, it's like, you get a very, very, you've got that model, like that diorama with the cloud rising off the sea, rain falling on the hill, running down in a river, and then into the ocean. That's the water cycle. It's like, the complexity of that, relative to the actual water cycle, is staggering, right? So, when we learn about computers, we're doing a very similar thing. Our mental model of how the computer actually operates and performs a program, executes a program, that's going to be different from how it actually executes the program, because the hardware manufacturer is going to do a hell of a lot of things behind the scenes that you don't need to know about to increase the speed of things, and branch prediction is one of these things. It's like, just, don't worry about it. As long as it's not breaking your abstraction, then it's fine. And that's actually, that's a general thing with programming, actually. Like, everything is okay as long as your abstraction isn't being broken. And the thing that was the problem with the Spectre bug is the abstraction was actually being broken. So it is a bug with concept, or the software engineer's implementation of concept. It's actually a hardware bug. Spectre is a hardware bug. But yeah, modern computers have a memory hierarchy of caches for improving performance. So you have different types of memory, right? You've got your hard disk, which is your most permanent and slowest memory. Generally speaking, with ways of storing memory, there's a trade-off between speed and volatility. So the faster the memory is, the more quickly it degrades. So you use highly volatile memory in the CPU and immediately around the CPU because it's being overwritten or modified or changed in some way several million times a second. So the fact that the memory is so volatile that it would probably lose its values in like 2 seconds doesn't matter, because no value is staying in it for more than 7 microseconds. So one of these types of memory is called cache memory, and it's used to accelerate CPU because you don't have to perform longer trips to the RAM. RAM is medium volatility memory. It's pretty stable, but cannot survive a power cycle, whereas your hard disk does obviously survive a power cycle, but it's the slowest memory to write to. So basically, to speed up the CPU, use the volatile memory as much as possible, which means storing intermediate values in cache memory rather than in RAM. So caching and cache memory is actually a very important concept in computing. Save or cache recently used values in the cache, so if we try to use them again, we can get them faster than loading them from main memory. Yeah, so this is all trying to speed things up. So what was happening with... I'll just go quickly through the rest of this. What was happening that was causing the Spectre bug? Well, these branch predictions were ending up in cache memory. But it turned out that if you had an attacker program, the attacker program shares the cache memory with this guy, right? Our victim program. So, if you executed a load operation at the correct point in time during branch prediction, you could load data into the attacker program that did not belong to it. This would be data from the victim program. And of course, most of the time it's who cares if it's your solitaire program? But if it's your banking information is always the the primary example, then basically violation of data policy is a big problem, because people are pretty clever, and if they can find a way to violate your data policy, they will be able to extract information you don't want them to have. Absolutely. Question: difference between cache memory and registers. Registers are very, very small, very, very volatile, and each CPU gets only about 16 of them, I think. Maybe modern CPUs have more than 16 registers, but registers are hooked up directly to the arithmetic logic unit. So, when you perform an arithmetic operation inside of the CPU, it gets operated on the registers. Cache memory is different. Cache memory, it's larger, right? You can store more data in it. It's not as fast as the registers because it's not hooked up directly into the ALU. But it's still reasonably adjacent to the CPU, so you can get pretty quick speeds out of it. Don't ask me what the particular type of circuit is. I think it might be SRAM. Or DRAM. I don't know. It's been a while since I've done an electronics course. Cache registers. God damn it. All right. Okay. Oh, it's 10:20. Let me just finish this. So, yes, the attacker program loads data that doesn't belong to it, and that's a big problem because then you can lose all kinds of information. There, we're done. Spectre bug. All right. Any questions? If not, get lost. Get off my lawn. Normies, get off my stream. You guys know I'm joking, right? You know I love you guys. Yeah. Now there's an interesting question which I can talk about for a couple of minutes. Mr. Freshly Squeezed asked, Nick, do you also teach college? What do you feel is the difference between the university and college comp sci programs? So I can tell you a certain amount about it. I taught in the college system a number of years ago. I believe it was 2018-19 that I was teaching in the college system. It was kind of funny. It was the college system was actually where I first applied to teach on a part-time basis, and that was sort of my that was me getting my foot in the door in the whole teaching profession. I was able to like work my way up to also getting university level contracts which pay a bit better, and in the college system I was teaching a writing course, which is a lot of reading essays, which is just not fun, and teaching math is more fun. So it was kind of like, well, the university pays better, and I would get to teach math, so easy choice. But what are the differences between the university and college programs? It's kind of interesting. I would say that, obviously, you would expect there to be more of a focus on application versus, theory. That's absolutely true. The college crowd definitely does more application and less theory. They do some theory, though. It's not, exclusively theory. But they don't really, the kinds of stuff that they would teach in, a second or third year algorithms class is, a third year college course over at Mohawk College. I was teaching at Mohawk College. But, so generally speaking, the program starts you off, you're not expected to pick things up quite as quickly in the college system. They have an equivalent, intro Python programming class in the college system, and I swear to Christ, they only go as far as, the end of this topic. Ish. I don't think they even get into data structures. I don't think they do tuples. Now, this could have changed since I was there a few years ago, but generally speaking, it's a pretty stable curriculum. So, but that's, the intro, and then it's, and you'd be surprised how many people do absolutely terribly in it. There are a lot of people who are, think that they could be programmers when they really don't have the chops. So it's for anybody who's, ever programmed in their life before, it's, easy 12, but you'd be surprised by how many people it filters out, even despite that. And then they have the second year Java course. They do Java in second year, and that's it's here's the real programming, guys. I understand. My understanding of the first year program is that there's a lot of you take an anthropology class for no specific reason. It's kind of you take some math, you take some general electives, and an intro programming course. But yeah, it's my general opinion of college people and the people in the college program as opposed to the curriculum is that the top end of the college cohort is competitive with the top bracket of the university cohort. Maybe I'd give a slight edge to the university crowd, but no, doing a college degree is a perfectly viable career strategy. They have courses on Android development. They focus more on the things that are in right now, whereas you guys will get a more theoretical education. Although there are moves in the department to try to bring more practical skills on board. 1XC3 is an example of that movement within the department to bring, they call it experiential education. To me, it's like, this is, in the style of a college. Pardon me. But, with the university program, we're kind of, some people consider IQ to be an invalid construct, but I'm going to use it for the purposes of this explanation. Generally, in the university system, you're expected to have a slightly higher IQ, which it means that you pick things up faster, which is why, this course will take us, this course will take us in the first month what it takes them 3 months to get to, because you're expected to be able to keep up with the pace. But yeah, so that's, I don't know, that's generally what I feel about it. How many caches can a cache register hold if a cache register could hold caches? Ha ha ha. Very good. Someone asked it this in assignment 2. Questions are regarding vowels. Do we include Y? Including Y as a vowel. Okay. If you can write an algorithm that correctly identifies when Y is a vowel and when it isn't, I will consider you for some extra bonus points. Otherwise, you may interpret Y as not being a vowel. Somebody in a linguistics class had a series of Pokemon-related questions on a worksheet, and I was wondering if you could include some Pokemon-related bonus questions in any of the assignments. Oh yeah, I had a final exam question a couple of years ago, where I asked people to basically do a highly stripped down version of the Pokemon battle system. So yeah, generally speaking, we'll see. Any questions, a question that specific about the assignment, please ask it on Piazza. Do you think the job prospect is the same after exiting college compared to university? That's a toughie. Generally, I would say the reason that you should be doing a bachelor's degree in computer science is that you have some ambition towards grad school. Just a bachelor's degree in computer science, bachelor's degrees are pretty cheap these days. They don't take you very far in the job market. That being said, there are certainly things you can do to augment that. Let's put it this way. The college system is pretty good at making sure that the things that they're teaching are precisely and exactly what the employers are looking for, because they are talking to the employers, right? It's like, looks like we've got a lot of companies in the area right now that are doing stuff with PHP. We need to do a PHP class, So because of that, entry-level positions, I would say college is designed to get people into jobs. University is designed to give you a higher level of education, right? So, it's kind of like, are you at a disadvantage for having gone to an institution that doesn't make, getting people jobs the primary purpose of the institution? Yes. Sorry, but yes. Does that mean, but a grad school, a college graduate would never have the opportunity of doing grad school, so. you know. And again, the department is trying to move things in the direction of giving you guys more practical skills as well. So that's the whole purpose of the reorg of the first year program, is to try to give you guys more co-opable skills, but and earlier on. But yeah. I regret not looking into college more because there's the stigma that you can't get a job unless you have a degree. Yeah, not very true, especially in like software. Um, you know, you hear stories about it, like in Silicon Valley, of like people dropping out of high school and joining up a tech company because they're really good programmers, and it's like, why would I waste my best years going to get an education that I don't need because I can just get a job because I'm that good a programmer? All the best programmers are self-taught, right? But yeah. Yeah. Oh, so you guys are a Pokemon crowd, eh? That's cool. I'm a Gen 1er. Um, hmm. Yeah. Yeah, so yeah, it's like, let me put it to you this way on the whole college versus university thing. Um, when my son becomes, gets to the age where he's um, considering what sort of post-secondary he will end up doing, I'm not going to push him into the university system, despite the fact that I have a PhD. Um, if he ends up, like, if he really wants to be a geologist, I will support his decision to become a geologist and go to a university for geology. I will cry myself to sleep, but he will be able to become a geologist. But like, if it's a job he wants, then I'm like probably going to tell him, listen, college is a perfectly viable option. There's no, like, I don't think the stigma will be there in 18 years. But yeah. Geomatics at Waterloo? Sure. Do I have Pokemon cards? Do I have Pokemon cards? I have the original Charizard card. Jeez, and I used it too. I knew how to play the game. I would play against my brother. What's wrong with geologism? I don't know. It's more like, what a geologist like, what problem do geologists have with me? Whenever I have like a student who's like hates me and my course, there's like a good 60% chance they're a geologist. If there are any geologists in the crowd, I'm not doing it intentionally. It's just how I am. Geomatics is where everyone who got de-referred from Waterloo CS. Sceptile is your favorite Pokemon of all time. I kinda like Gyarados. Gyarados is pretty solid. Show you the card. They're in the attic. I gotta pull out the cards, but... yeah. Okay. So... quick... I was born in 1988, thank you, sir. I was born 1988. I'm older than I look. I'm an elder millennial. Because the cutoff for millennials is 1985, so I'm like the third year of millennials. Yeah. But yeah. So Gen 1, you can't even put it on the scale because it was so different from every video game that had ever been that it opened a new category of video games. So Gen 1 cannot be compared to anything. It doesn't even rate, right? It's apples and oranges. Gen 2 was truly excellent. Although the fact that it didn't quite live up to the claim of having both the Gen 1 and the Gen 2 maps in it was a bit disappointing, but it was still an excellent game. Number 3, Gen 3, possibly my favorite. Gen 4 was good. Not as good as Gen 3, in my opinion. Gen 5 was, like, that was Black and White, right? Diamond, Pearl, Black and White. Yeah, Black and White was hot garbage, but then Black and White 2 was the best game in the whole damn series, not including the first ones, like, which, again, you can't put on the scale. So, yeah, Black and White 2, masterpiece. Masterpiece. X and Y, hot garbage. Sun and Moon, hotter, stinkier, smellier garbage than X and Y. Sword and Shield, I don't even know why I bought them. And I haven't bought a Pokemon game since, and I might not. That's how bad Sword and Shield are. I hate what they've done to the Pokemon games. I hate them. I want them to play the old games again. Figure out why they were good. Ugh. I have opinions. What about the new one, Legends of Arceus? They still haven't learned their lesson. Okay, alright. Alright, Pokemon guys. Alright, the Pokemon Company, I hope you're listening, because I'm about to tell you how to fix your Pokemon games. Nobody cares about the human characters. Nobody cares about the human characters. Nobody. All we want is more Pokemon. We don't care about Tanya or Jared. Just give us more Pokemon. Alright, I think that's enough goofing off for today. Take her easy, folks. I'll see you in the next one.